Well, good morning, everybody. Sorry about the technical difficulties. Everything was broken. And now I'm on the backup of my backup. Oops, no, don't do that. Do this. There we go. So, welcome back. After last week's exam, oh boy. More on that on Thursday, right? You can still come talk to me about it or email me about it if you want, but we'll do the exam autopsy on Thursday. I couldn't believe I almost forgot this. Darn it. We got something amazing happened this weekend. Where was it? Right here. Okay. We have to watch this. All right. So, if you haven't heard of SpaceX, you've been living under a rock, right? But that rocket right there is the largest rocket that's ever flown. Okay? It's taller than 2 space shuttles. It's about as big around as this room is wide. The Saturn V, which took us to the moon, is a little bit shorter than that thing, right? Watch what SpaceX did. This is like, this is a historical moment for engineers everywhere. Play. I hit play.
3, 2, 1. We have liftoff.
That's millions of pounds of thrust pushing that thing up. Like, it's just incredible.
Downrange.
This is how we're going to get to the moon. This is how we're going to get to Mars. There's 33 engines on that rocket.
Gorgeous things I've ever seen in my entire life.
So it's getting up, and it's going to separate the Starship, which is the pointy bit, and then the booster turns around and comes back. We've seen SpaceX do this before with their Falcon 9s, right? The little tiny rockets. They caught a 12-story tall, 9-meter wide rocket out of the air with a pair of very large chopsticks. Right? Like you have, it is really hard to express the engineering challenge that we just witnessed, okay? That was the 3rd test. The first test ended with a big blow up, they call it a rapid unscheduled disassembly, way up in the upper atmosphere, okay? No pieces were left after that one because they lost control. The second one landed in the ocean, pre-planned landing in the ocean, and was within a centimeter of where they wanted to put it, okay? So the 3rd time they decided to go and catch it. 5-6 years ago when SpaceX proposed this as their landing system, experts in the field everywhere told them that they were crazy and that they were going to go out of business trying to attempt this. They did it anyway. Like, kudos to all those engineers that worked so hard for so long to make that possible. That is just mind-blowing. I mean, you're not gonna. Maybe you'll go work for SpaceX. I don't know, but it's kind of part of the reason you're here, right? You're in a major like this one is to be able to be a part of things like this, right? It doesn't have to be rockets. It can be climate change. It can be cars. It can be heating and ventilation systems. It could be building roads and bridges or building like what we humans are able to do when we come together and put our minds to it. Is absolutely incredible. I know that there are terrible things happening in this world right now, but there are also really, really good things happening. And this is just one tiny, amazing thing that hits our engineering side. All right. If you look at the schedule, you'll notice that this unit is slightly shorter than the other units. In other words, I think for the first 2 units, we had about 4 weeks of content before we took an exam. This time we've got 3 weeks. And I need to start cutting some corners. And this is one of the places I cut the corners, okay? We're not going to do two-dimensional collisions. You're welcome. And then rocket propulsion, I will talk about when we actually do like gravitation and orbits and how to get to different places in the solar system, which I think is chapter 13, if I remember correctly. Okay, so we're gonna punt, right? Rocket propulsion, and we're just not going to do 2D collisions. You're not missing out when it comes to 2D collisions. It's just basically, I'm going to teach you how to do a bunch of vector stuff with momentum, and then just do that in x and y instead of just x, okay? In industry, in engineering, especially in computer game engines and computer simulations, all momentum problems are one-dimensional anyway. Even if they look two-dimensional, it's actually faster to treat them all as one-dimensional problems. You just rotate your axis, do it on one dimension, and then rotate it back and figure it out. It's a slick trick in computers. Nobody does 2 dimensions anymore. And I'm not sure why they make us do it. So we're going to skip it. All right. So what's momentum? It's a good question. What has more momentum? A train moving along the tracks or a car moving along at the same speed? The train. Why does the train have more momentum? It's bigger, right? Okay. Like it takes more work to stop the train. Like you have this sense, an idea, right, of what momentum is. Mathematically, whoops, got ahead of myself. Momentum is an object's mass times its velocity. Okay. What are things that you notice right away? The vectors are back. We bid them goodbye, didn't we, for like chapter 7 and 8? In energy, they were kind of there. We had to be careful about our directions with force and displacement to get like a negative work and things. But like, really, we didn't have to worry about x's and y's and components and things, okay? So the bad news is vectors are back. The good news is they're not as bad as they were in, say, chapters 5 and 6, okay? So we will have component. We've got to deal with that. Mostly, we're going to deal with this by just making sure we're careful with our directions. If something changes its direction, we have to make sure to put a minus sign, that kind of thing. All right. Momentum is the last major toolbox that we are learning in Physics 4a. What have they been so far? Let's see. Kinematics, that was the first toolbox we started with. Then Newton's laws. Then energy. And now we've got momentum. There's a 5th toolbox we will teach you. It's called simple harmonic motion, but that's going to be in Physics 4c. So when it comes to momentum, it's a vector. It's spelled with a P. I would apologize for that, but it's not my fault. And it is a conserved quantity. What does that mean in the context of physics? You can't really lose or gain momentum. You can only trade it. Now, when it came to energy, that's true like on a universal scale, and it's true on a universal scale with momentum, but momentum, you do have to be a little bit more careful. For example, if I've got my car, right, and I'm driving along at, 30 miles an hour, and I come to a stop. Okay, did the car have momentum while it was moving? Yeah, right? It's got mass, it's got velocity, right? And then I applied the brakes, and it came to a stop. How much momentum does it have now? 0, right? It's not moving, so it has no momentum. Where'd the momentum go? Friction isn't like an object, right? Momentum would have to be transferred to something with mass and a velocity of its own, right? We've got to be trading. So where did it go? And this is something that a lot of people don't really consider, right? The Earth took it. Okay? And you're like, well, the Earth isn't moving. Well, it is. Okay? But we can kind of narrowly define what our system is. And in doing so, we can kind of make it look like momentum's not conserved. Like if we just call our system the car, then yeah, it looks like momentum before, momentum after didn't work. We have to either broaden our definition of what our system is or be careful about how we apply conservation of momentum. But we'll get there. We will get there. Where does this kind of come from? Just to give you some insight, you don't need to write this down, okay? You remember this? Unfortunately, right? Okay. So it causes a lot of problems on the exam. Definition of acceleration is what? Good. Change in velocity over change in time, right? And then if we kind of move that constant of mass in there, which we can certainly do because it's just a number, it's not going to change that change. I know you're looking at that like it's a derivative, Mr. Bailey. You're not wrong. It is a derivative. But like, notice that we have a change in something, an mv, which we now know is a change in momentum. So if you are going to change the momentum of an object, what needs to happen? Force, right? A net force, the non-zero net force, I mean, take all the forces on an object, add it all up, that can't be zero. Car is moving, had momentum. Car comes to a stop, has no momentum. What needed to happen? The force of friction. Now we're talking about forces, right? Newton originally defined his second law in terms of momentum. That's where he started. Concepts of mass and acceleration came a little bit later for Newton. Galileo had nailed down acceleration, velocity, all that kind of stuff. And of course, Newton knew about it. But when Newton first sort of formalized his ideas about how forces cause objects to change their motion, he conceived of motion as momentum. It was this combined idea of an object with mass and its velocity. Change its speed or direction, and something had to cause that change to happen. That something is a force. And that force has to come from an object. Now, interestingly, there's something along for the ride besides just force here, right? We've got a change in momentum, but we also have a change in... Okay, so now we've got time. Time is back. Right? And now this is a little scary, right? Because the last time we ran into time was kinematics, wasn't it? Yeah. And a little bit with power, right? With energy, we were able to kind of weasel some time in there to get watts, right? Power is equal to energy per time. But now we're mixing forces, we're mixing time, we're mixing this concept of momentum. There's kind of a lot of stuff that can be going on here. So let's try to disentangle this, right, by talking about what most people concentrate or confuse momentum with. So this is kind of a warning. This is a big trap, conceptual trap. It's an intuitive trap. It's sort of something that you'll see here in a second. You're like, oh yeah, no, I see that, Mr. But you'll confuse momentum for impulse. And what is the difference here? So impulse, strictly speaking, and there's different symbols for this. I forgot to check your book. Does your book, I think it uses capital I or J? I don't remember. There's a J? Yeah. Okay. The impulse, okay, is a change in momentum. Now there, I'm using my my delta, right? When we did Newton's, when we did the change in momentum over time is equal to some of the forces on the previous slide, right? I can, well, just to show you a little bit of calculus here, I can take, I can separate out those two different changes, and now if I want to add up all the changes in momentum, what I do to one side, I have to do to the other, right? So a change in momentum, that integral of a little tiny d turns it into a delta. This becomes, assuming that the force is constant and doesn't change in time, right? You get this relationship between the change in momentum, force, and time. We'll get to that in a second. Impulse is a change in momentum. And what's a change? What does delta mean? It's final minus initial. So notice that there's vectors there, right? Impulse being the change in momentum of a system. So that's true. What is also true is that impulse, force, and time are all related to each other. Let's do some what ifs. I didn't bring a mug with me. So imagine like a coffee mug, right? Okay, ceramic coffee mug. And I've got it here on a table, and I'm going to test drops on two different kinds of floor. Okay, so we'll have a tile floor like what you might find in the kitchen, and then we'll have like a carpet, right, which you might find in the living room or something, right? And if we push the coffee mug off the table, okay, so it basically kind of starts with 0 speed, and it goes down and lands on the tile floor versus landing on the carpet. Very carefully answer the following question. In which case the tile floor or the carpet is the impulse bigger? What's impulse? It's a change in momentum, right? The answer is it's the same. It's the same impulse regardless of whether it's tile or floor. Now, your brain, where did it go? What's harder, right? And whether or not the cup's going to break. What of the three things in that box right there is going to determine whether or not the cup breaks? Force, right? How much force is applied to the cup is what determines whether or not it breaks. I didn't ask you for force. I didn't ask you on which surface does it break. What I asked you was, what is the change in momentum? What is the impulse? What is the cup doing in both cases? What's its speed right as it hits the ground? Whatever it is, right? But is that different for carpet and floor? No, it fell through the same height, right? It will have the same speed in either case. So what's different? What's different about the tile floor versus the carpet? The tile stops it faster?
Something compared to the carpet, yeah.
Okay, what words would we use to describe why the carpet doesn't break the mug? It's soft. It cushions the fall. Right? Okay. What are we talking about here? Say what you did. No, the other one. Time. Talking about time. How much time does it take for the carpet to stop the cup compared to the tile? More time. Why does it take it more time to stop the cup? It's got to compress all that carpet fiber and the pad and all that kind of stuff, right? Our impulse is the same. The change in momentum is identical in both of those situations. What's different? The amount of time it takes for that impulse to happen. So what's the trap in your brain, and where's the intuition, where's the bad information? People tend to associate like the momentum with the impulse. And especially when it comes to collisions. We're going to be talking about collisions in this chapter. This is basically all it is about. When objects are coming into contact, the confusion between the force that's applied, the momentum something has, and its impulse, which isn't the momentum. What's impulse? Change. Oh, so hard, right? Change in velocity. Like, it's not the velocity, it's the change of. the change in momentum, the force that's applied to the object, and the time it takes for all of that change to happen matters. Okay, so let's do some more what ifs. I got so many examples of. Okay, let's biology. Okay, let's just talk some biology here real quick. Okay, I'll do this off the table. All right, so I'm going to jump off the table, right? Okay, I will demonstrate the correct way to jump off the table for a 50-year-old man. You ready? Okay, don't do it. No, most people want to see their physics teacher hurt. Okay, all right. So here we go, right? Watch. What did I do? I bent my knees. I did quite a deep squat, right? Okay, why?
Increase the change of time to less force.
Okay, so now I'm going to get up on the table and I'm going to jump off, but instead of bending my knees, I'm going to lock my knees before I hit.
No, don't do that.
Okay? Your face has said it all, right? You know what would happen if I did that, right? I would shatter the bones in my legs. Okay. Which example had more force? Locked knees had more force. How do you know?
There was less change of time.
Because all my bones broke.
Yes.
Right? Like, it's obvious. Like, did I just break any bones? Am I going to have to do physical therapy after? Well, yeah, I'll have to do physical therapy for my back. But, like, I didn't break anything, right? But if I lock my knees, I'm definitely breaking something. There's obviously more force in the locked knees. So, the impulse. Which one had more impulse? How easy is it to say the one where you broke your leg? It's not the one where you break your legs, right? The impulse is the same because I'm jumping from the same height, right? I hit the ground. Because I'm leaping from the same height, I have the same speed when I'm coming to the floor, and the floor is going to bring me to a stop, right? So the impulse there is all the same. So if the force is bigger, force go up, and impulse is constant, what does the time have to do to make the force go up? It's got to go down. Force and time are inversely related to each other if the impulse is the same. We'll get to some examples where the impulse isn't the same in a second. Try not to make this any harder than it is. The confusion stems from not being careful about distinguishing between momentum, which is the motion of an object, and the change in momentum, right? How is this object coming to a stop or bouncing off of a surface or another object? Be careful. Don't assume that your intuition is going to connect you to the right idea. Really get into the definitions, right, about what I'm talking about. Change in momentum, which is the impulse, force, which is a push or a pull, and then the amount of time that all of these things are taking place. Let's do the example. Okay, so let's do an example where the impulse is different. So, and I apologize in advance for the violent nature of all the examples in this chapter. We are talking about collisions, and what's the very first thing that pops into your brain when you hear the word collision? Cars, right? So, in all seriousness and with all due respect for any of us that have been through the trauma and violence of a car accident, that's real, right? It hurts. It is not fun, right? But I will now go and make a bunch of jokes about it, okay? So, in an accident, okay, so you should know something. Just about every car since the early to mid 1990s has come from the factory pre-broken. Do you know this? Some of you are like, I knew I got a lemon, right? No, what do I mean they come pre-broken? Yeah, the crumple zones, right? Engineers, okay, so I learned to drive, I learned to drive in the 90s. But The car I learned to drive in was an International Harvester Scout 2. Now, for those of you that don't speak car, what that was a tractor that they decided to make look like a Jeep. Okay? It was built in the early 70s out of Detroit in an era when they told people who were making cars, they gave them a solid block of iron and a chisel and said, make a car out of that. Like my Scout, if I hit something, the other thing lost. Right? Like my car was a solid hunk of metal. In fact, you could take the front grille off and there was a power takeoff for farm equipment right there. I had a compound low first gear, which means in first gear I could take my foot off the clutch and the car would idle up a 20-degree slope. No gas. Right? Like I had torque out the wazoo. There were 4 gears in that car. I usually started from a dead stop in gear 3. Okay? So I had 2 gears available to me. But cars from that era, okay, had a big problem. If you hit something at 30 miles an hour, okay, there were very likely going to be body bags at the scene of the accident. Nowadays, cars can be involved in collisions at 60, 65 miles an hour, and you'll have people walking around at the accident scene on their phones calling their lawyers. It's really incredible. My car, if I had done a crash in it, I would be dead, but the car would be fine. Crashes nowadays, I mean, come on, you pull a car up in a parking lot and you hit that little piece of concrete that's supposed to keep you from going, right? And the whole car falls apart, right? Bumper, airbags totaled, right? Okay? Why are cars so sensitive? Why do they fall apart? Why is it that when you see an accident nowadays, there's all these alive people, but car parts are strewn all over the place? Value life over the car? Not in the 70s, right? We've progressed, right? These crumple zones, what are they doing? What are they doing? Can we affect the impulse? A car going at 65 in a crash is gonna end up at 0, isn't it? Eventually. So what's the only other thing we can play with? Force and time. How do we get the forces to be low? Increase time for all of that change in momentum to take place. So the car will crumple in its engine. Is there anything important in the engine? Well, yeah, make car go. But like compared to human life, no. Right? Is there anything important in the trunk? No, right? So keep the smushy parts, the squishy things safe inside of a cage and let the other parts of the car crumple around them, increasing what's an airbag for? Increased time of what? For you to come to a stop. For your momentum to change. Because if we can increase the time it takes for your momentum to change, what can we decrease? The force acting on you. Those of us that have ever had an airbag go off in our faces know it does not feel like a reduction in force. It feels like being punched in the face. In fact, what has happened is a small pyrotechnic has gone off in your face. Like something bigger than a firecracker has gone boom. That's how the airbag inflates so quickly. And it hurts, and you get bruised, and the car fills with this smoke. It's a powder. It's the talcum powder that the bag has been packed in to make sure that after 20 years it can inflate fully without bursting or anything like that. So you're choking to death because the air is filled with dust. Okay, you've been in this accident. You've been punched in the face. Okay, and you're disoriented and your ears are ringing and all kinds of stuff is happening, and you get out of the car, but you are still able to walk around. It's really incredible. Wear your seatbelt. It's the other thing that keeps you. Okay, most people nowadays die in car accidents because they are ejected from the vehicle, not because of anything else. And if you're ever in a car accident, try to have the wherewithal in your brain to watch yourself and other people. You will be in shock. Other people will be in shock. And the most important thing, this is not me being a dad, this is me being an emergency medical technician. There are 3 collisions in a car accident. Can you name what they are? Car hitting other object. What's the second one? You hitting the inside of the car. So the car is stopping, but you keep going. Why do you keep going? Newton's first law, right? Okay. So now you've hit, hopefully, the airbag, the seatbelt, something, right? Okay. What's the third collision? Internal organs striking the inside of your body cavity. Your body's coming to a stop, but everything else, all the smushy bits, continue going. Okay. So you arrive on the accident scene, you're part of the accident, whatever's going on, watch the people. If they are turning white, if they are getting dizzy, and if they start fainting, it's a good possibility they have internal bleeding. That is the most important thing to take care of, right? 911 all the way, get that person some medical help. This lecture has gone dark. While we're in the darkness, let's talk about guns. Pistols versus rifles. Which type of gun will send a bullet faster and therefore further? A rifle. So the whole reason rifles exist is because they have those long barrels, right? Compared to a pistol that has a shorter barrel, okay? So we take identical bullets, right? And we put it in a pistol and then we put it in a rifle. The bullet coming out of the rifle will be going faster. What's the same now in that relationship right there? The force is the same. Why is the force the same? Same bullet, same amount of gunpowder that pushed the lead out, right? Okay? So that force is the same. We know the impulse is different now. How do we know the impulse is different? Rifle make bullet go faster, right? Same mass, bigger speed. So the rifle gave more impulse. So if the force is the same, but there was more impulse in this example, what happened to the time? It increased. Force same. We want bigger impulse, so what do we have to do with time? Bigger time. How did the time increase with the rifle? Longer barrel, right? That longer barrel gives more time for those expanding gases from the gunpowder to push the bullet out. Pistol, not as much time. So there's an example where the impulse is different and the time is different and where the force stays the same, right? So those are the kinds of thoughts you've got to keep track of in your head and make sure you have the definitions down for. And force and those are much more made up.
So the only time where impulse will change is if force is the same.
Really, we're playing with force and impulse. It's the relationship between force, impulse, and time that we're playing with. Try to identify, or maybe it's better to say, it's more critical to identify the thing that's staying the same. Right? Am I comparing two impulses that are the same, like the coffee cup, like the car, right? Or and therefore force is different? Or is force being kept constant and now we have different? The way you know is look at the impulse. Compare the two situations, and if they have the same speed and come to zero or whatever's going on.
And also, is momentum a force or is momentum
Momentum's a momentum. Yeah, it's a force times a time, which didn't help, but yeah. Momentum is the quantity of motion an object has. Tastes like salt. All right. Other things to realize about impulse. It's a vector. If an object is moving, Let's say we throw a ball against the wall, okay? And we say its initial velocity is positive to the right, okay? We put that plus sign, which means we've now said this is our positive direction, okay? Let's say it's moving at, I don't know, 10 meters per second, okay? And it bounces off the wall at 5 meters per second. How do I calculate the impulse here? What's the final momentum? Well, it's going to be the mass. Okay, so let's give it a mass. It's a 10 kilogram. Well, that's a big ball. Okay. So it's going to be mv final minus mv initial, right? So it's going to be 10, and then v final. What do I write down for v final?
0.
Well, no.
5 meters per second.
5 minus 10, and then what do I write down for v initial? 10, which gets me, this is a negative 150. That's negative 50? Did I do that right? What are the units? Wait, let's talk about units later. Let's talk about this. It's more important. This is wrong. Wrong, wrong, wrong. Why is that wrong? I wasn't careful about directions. Which way is the 5 going? It's in the negative direction. That's where the vector part comes in. Okay, it's not so much a component as it is a direction that's associated with it. So if I want to do this correctly, this would be 10 times a negative 5 minus a 10 times a positive 10. And now I get a negative 150. And that would be correct. Mind your directions when it comes to impulse. If something bounces, it's changed its direction. Yeah?
There was a problem in the home where it was like a skydiver or something, or a parachute was falling through snow. And wanted to find the distance he fell.
Yeah.
How do you find a delta x from this equation?
You don't. That's conservation of energy. Yeah. The work equals force times distance. Units. What are units of momentum? Remember, momentum is mass times velocity. So unit-wise, what's a mass? That's a kilogram. What's a velocity? It's a meter per second. So what's a kilogram meter per second? Well, it's not a Newton. Because a Newton's a what? Kilogram meter per second squared. So what's this called? Half a Newton. A semi-Newton. Actually, no, it doesn't have a new name. That's just what it is. The units of momentum are kilograms meter per second. Which I think there's a big opportunity here, isn't there? We could come up with a unit. Maybe we could call it a Balogh. Is a kilogram meter per second? Can we just say Balogh? Capital B? Unfortunately, that symbol is reserved for something else in physics 4B. More importantly, what's the plural form of Balogh? Baloghs or Balonians? Maybe we should stick with kilograms meters per second. All right. It's a kilogram meter per second. There's no other name for that unit. That's just what the units of momentum are. So this would be negative 150 kilogram meters per second. So mind your signs. Be very careful about when things are bouncing. Be sure you can identify the thing that's being kept constant in the momentum, force, time relationship. All right. What are these? Those are safety barrels. They're filled with water or sand. The purpose of a safety barrel is what? To prevent death? Yeah. To Okay, well, I'm a cynical person, so I would say the safety barrels are there more to protect the pole than the person who's running into it. Because, I mean, ostensibly, you should not be running into poles on the side of the road, right? Okay. But yes, we get the added benefit of protecting not only the pole, but the person that's trying to run into it. Right? How does it work?
Increases your time.
It's playing with time, isn't it? The change in impulse is going to be whatever the change in impulse is. Car moving, car come to stop, right? We can't, whether the barrels are there or not, that's going to happen, right? So in this sense, in this example, we have a case where the change in impulse between the two situations is going to be the same. So let's see what happens, okay, with somebody going about 55 miles an hour, right, with and without safety impact barrels. And I've guessed that the time of impact, the time it takes for everything to come to a stop, right, all the pieces to stop flying, whatever's going on, is half a second. That's actually probably too long. It's probably much faster than that, okay? But again, sort of making stuff up here, right? And then we're going to compare and contrast that where we add some safety barrels which extend the time of impact by 1 second. So the total time of impact would be 1.5 seconds. We're just going to find the force in these two cases, right? So we've identified that what is staying the same? Is the time the same? No, one's half a second, one's 1.5 seconds, right? So we're looking at the relationship of impulse, force, and time, right? And we're comparing two cases. We've got a red case and we've got a blue case. Okay, where we got some extra time, right? This is the 1.5 second case, and this is the 0.5 second case. Okay, so what's the same? Impulse. Why is the impulse the same? Yeah, what's the initial speed of the red one? 25 meters per second. What's its final speed? 0. And for the blue one, how fast is its initial speed? 25 meters per second. And what's its final speed? 0. So there, and the mass is the same, isn't it? So the impulse is going to be the same for both of these cars. Matter of fact, we can just go calculate it. I'll do it in black, right? The impulse is going to be the final momentum minus the initial momentum. I got to remember it's a vector. Okay? So a lot of times we write this as m and then quantity v final minus v initial. What just happened there? Mass is in both of them, isn't it? So just factor it out. Save yourself some time. Okay, so there's 1,500 kilograms, so 3,000, 4,000-ish pound car. V final is what? 0. Minus, and if we say the car is moving to the right when it hits the wall, okay, then we could say the initial speed was positive, so that'd be minus, it's final minus initial, right? So the minus sign is coming from the difference, the delta, but then it's a positive 25 because it's moving in the positive. How easy is it to make a sign error here? Very easy, right? Be careful. So this turns out whatever negative, is this 75, what is this? Negative 37,500 kilogram meters per second. Okay, so that's what the impulse is for both the red and the blue. So to solve for the force, I divide both sides by time. Now cancel over there. So my force is going to be my impulse divided by my change in time. So for the red one, the force is going to be my impulse, negative 37,500, all over the time, half a second. That's 75,000. So 75,000 newtons for the half second collision. And then I do the same calculation down here for the blue. It's the same impulse 37,500 divided by 1.5. Now notice I put a negative sign in here because the impulse was negative. But what does the negative sign mean in this case? Force equals negative 70. Which way was the force? It was opposing the motion, right? So the force magnitude is 75,000, but it was just to the left, right? It was moving to the right. The force had to be applied to the left to get this thing to come to a stop. Okay. Ooh, mixing my colors. Don't do that. This turns out to be 25,000 newtons. So the difference is a 50,000 newton difference. That's approximately 11,000 pounds of force. So by adding 1 second to this collision, we've saved the car, the occupants, the pole, everything. We've saved 11,000 pounds of force. You woke up this morning, somebody says you have a choice. You can experience an extra 11,000 pounds of force today or not. The answer is no, right? Because 11,000 pounds will crush you, right? So, important safety tips, right? So again, hopefully that was just an example, right, of dealing with impulse and being careful with your signs and all that kind of stuff. Let's do a quiz. All right. Collisions and conservation of momentum. How do we conserve? Oh my gosh, I forgot something. Oh no. Okay, I'm going to let you look at this slide while I go get the thing I forgot. I can't believe I forgot this. I am just a bad teacher. I'll be right back. All right. Many of you have seen something like this before. This is a big version of like those desk toys things, right? And what do? You take one of these balls and you let go, and what happens? CEOs across America have these on their desks. They have no idea what they're for. This is called a Newton's cradle. Okay? If I take one, and these are all identical billiard balls here, and if I take 1 units of momentum, right? If I let go from here, it's going to have a mass times a velocity. Where does that mass velocity go? To the next ball, then the next, then the next, then this one comes out, right? So if I do 1 in, I get 1 out. You can see I'm losing momentum and energy here to sound and some other bad things. Okay, so that's all fine and good, but let me show you how to get the job in the job interview. You see one of these on somebody's desk during a job interview, don't even introduce yourself. Say, oh, this is amazing, let me show you what this thing does. What happens if you send 2 in? 2 come out? Momentum is a conserved quantity. So 2 in means we have to have 2 out, right? So let's see what happens. 2 in equals 2 out. Okay. What about 3? 3 have to come out. But there's only 2. You ready? 3 in equals 3 out. 4? 4 in equals 4 out. What about 5? It works. All right. This is a conservation of momentum apparatus, right? It's really interesting because 1 coming in doesn't equal 2 coming out at half the speed. It's not like a conservation of mechanical energy apparatus. It's a conservation of momentum. 3 units of momentum in equals 3 units of momentum out. Always. Momentum is conserved. Now, in the case of these balls right here, which kind of collision do we have? Inelastic. What's the difference? What's the difference between those two?
One of them is deformation.
The really kind of the only difference is kinetic energy, isn't it?
Yeah.
Okay. Oh, we're being visited by a geologist. Good morning.
I'm interested.
Okay, good. Yeah. Well, do you use stuff in geology like physics?
Yeah, I think it's geophysics.
Geophysics. That's right. It applies everywhere.
No fun demonstrations like this.
Well, could you have rocks?
You send seismic waves through the earth and record.
That's a pretty good demonstration. Greg James and everybody, thank you.
Great, I love this. This is
Yeah.
learning. Thank you.
All right, so the big thing here is kinetic energy, right? What's the difference in kinetic energy? Conservation. Okay, notice this is not saying conservation of energy. Energy is always conserved, right? Full stop. Kinetic energy specifically is not conserved in an inelastic collision.
In our billiard balls, it's neither elastic or fully inelastic because there's sound and stuff, but
Okay.
a lot of it's being considered.
Liam used the words fully or completely. And this is something that physics authors and physicists do to trick people. A completely or fully inelastic collision, by definition, is one where objects stick together. Sorry, that's just the way we define it. Okay? A completely elastic collision means that kinetic energy is conserved. That's just kind of the language that's used. More generally, inelastic collisions are the everyday collisions. 99% of collisions that you will ever experience or work with is going to be inelastic. Okay? What are some examples of like natural, in nature, in the universe, elastic collisions? Because they're often considered to be like the perfect collision where everything's conserved, everything's tidy. Billiard balls is close, but there is a source of energy loss in the billiard balls. What's the big source of energy loss? Sound. Okay, so we will now do this. We will do this experiment in a vacuum. So everybody, hold your breath. No. Okay. But if I could get rid of all of those energy losses, this, in theory, should go forever, right? Okay. Here is the most perfectly elastic collision I can demonstrate to you right here on the surface of the Earth. Okay. I'm not talking about the collision between my hand and my keys. I'm talking about the collision between my keys and the Earth while it's in the air. Wait, but Mr. Balogh, when it's in the air, it's not colliding with anything. No, it is. Because what's a collision in physics? It's any interaction between two objects. Did the keys experience a force on the way up and the way down? Yeah, what is it? Gravity. The keys are colliding with the Earth on the way up and the way down. They collide with my hand later. If I let them hit the ground, then they collide with the ground, right? But the collision that's taking place all the way up and all the way down is one with the Earth, and that is a perfectly elastic collision. We use perfectly elastic collisions, in quotes, to sling spacecraft around the sun so that they pick up speed so they can get to the outer solar system. The gravitational slingshots of orbits and things like that are all perfectly elastic collisions. Here on the surface of Earth, where we tend to have friction and loss due to sound, deformation, things changing shape, things sticking together, like the objects sticking together is like the biggest deformation you can have in terms of the masses of things, right, going places. So Generally, so what we do for chapter 9 at this level is we try to make it really clear to you in the problem. They'll say, 2 cars collide and hook their bumpers together. Well, now what do you know? It's inelastic, right? 2 cars have super powerful magnets attached to their fronts, and they collide with each other but don't stick and bounce off. It's probably elastic. But even more so, if you're ever confused, you just ask me. I tried to pick homework problems where it would tell you, right, if it's elastic or inelastic. They'll say 2 objects collide elastically or assume an inelastic collision. Like, it would just kind of tell you straight out, right? The big difference here being, with elastic, you can write down a conservation of kinetic energy equation, which you cannot do with an inelastic problem. So most of the time, we're going to be inelastic, and we're not going to be able to use conservation of kinetic energy. We can use conservation of energy, but we just can't use conservation of kinetic energy. I know that sounds weird. I'm going to show you the next slide. You're going to freak out. It's going to be okay. Because every problem in chapter 9, really any problem in physics anywhere, but especially chapter 9, is a sandwich. You're often doing 2 or 3 problems per problem when it comes to conservation of momentum. What do I mean by the sandwich? I like to think of this as the meat or the vegetables or whatever the thing is between the 2 pieces of bread, right? So the peanut butter and jelly, okay, is the collision. It's the conservation of momentum. It's the thing that we're learning in this chapter. It involves impulse, it involves force, it involves time, all those things, okay, is right there in the middle. The 2 pieces of bread on either side can be from different toolboxes. If we want to be able to identify what's going on in the collision between 2 cars, we need to know how fast they're going when they hit each other, right? But what if one rolled down a hill? How do we find out how fast a car is going if it rolls down a hill? We have to use kinematics or Newton's laws or conservation of energy. We have to reach for another toolbox for that, right? The conservation of momentum toolbox, momentum initial equals momentum final, the chapter 9 stuff only happens in that short time period where the objects are interacting with each other. Before that and after that, it's whatever toolbox we want to use, whichever one we find the easiest to apply in any given situation. Okay? So just realize that about the problem solving in this chapter. It's a minimum of 2, if not 3 toolboxes, right, that you will be applying. Being able to identify the collision itself and then what's happening before, what's happening after becomes really critical. I'm out of time for today. I was going to try to do an example, but I didn't. I had technical difficulties instead. So on Wednesday, we're going to finish up chapter 9. It's going to be just a bunch of examples. Inelastic examples and 1 elastic. I'm going to give you a key, a shortcut to solving all elastic problems. And it'll save your bacon. I will see you on Wednesday.